Okay. Hello, everyone. Today in this session, we're going to have Tuğba Yesin to have her talk about something that I don't even have any idea. But before starting, we want to learn more about Tuğba Yesin's personality and what she is doing right now and as her studies. So Tuğba, who are you and what are you doing? Could you please tell us more about yourself?
Hey, hello everyone, my name is Tuğba Yesin. I'm a last year PhD student in mathematics department at Sabancı University. And I'm working with Dr. Mohammed Sadek. And my research interest is mainly number theory with focused on elliptic curves and arithmetic of dynamical systems. Should I share the screen?
Yeah, I think that was enough. Thank you. We can start now. You can share your screen.
Okay. All right.
Yeah, we can see it. You can start now.
Okay, thank you. Today, I will talk about the divisibility by 2 on quartic models of elliptic curves and rational Diophantine D quintuples. First of all, this is the work, joint work, with my supervisor, Dr. Mohammed Sadek. Firstly, I will mention about the Diophantine M tuple. What are these tuples and D quintuples? The Greek mathematician Diophantus of Alexandria first studied the problem of finding 4 numbers such that the product of any 2 of them increased by unity is a perfect square. And he found these first 4 rational numbers satisfied this property. I mean, if you take any 2 of them and the product plus 1 should be square, as we saw here. After that, we can ask if we can find 4 integer numbers that satisfy the same property. And Fermat found these 4 integers, 1, 3, 8, 120, satisfied the same property as here. So with these 2 examples, one is from the rational numbers, one is the integer numbers, we can see the definition of Diophantine M tuple and the rational Diophantine M tuple. What are these? A set of m positive integer from a1 to am is called Diophantine M tuple if ai times aj plus 1 is a perfect square for all I and j from 1 to m. Here I cannot equal to j. In that case, it's called strong Diophantine M tuple. This is another field. There are many works on this field. And we can define this Diophantine M tuple for the rational numbers. If we take m rational numbers satisfy the same property, we will call this set is the rational Diophantine M tuple. Okay, what do we know about these tuples? I mean, if we have a tuple, if we have a pair, Diophantine pair such that 2 and 12, for instance, 2 times 12 plus 1 is 5 square. So can we get a triple by using this pair, or can we extend from triple to quadruple? The first question from pair to triple, this is yes. If we have a Diophantine pair, AB, that can be extended to Diophantine triple, by adding this number, a plus b plus 2r, r satisfied this equality. As I give this example, by using 2 and 12, if we add 24 to this set, we can get Diophantine triple. And the next question will be next extension from triple to quadruple. Can we get this extension by the same way? Yes. If we have a Diophantine triple ABC, that can be extended to Diophantine quadruple. How? If we have Diophantine triple, we have these 3 equations with r, s, t are the positive integers. And then by using one of these, d plus or d minus, this equality, if we add this set, this number, d plus or d minus to this set, we can get Diophantine quadruple. For instance, for 12 and 30, which is Diophantine triple, we can easily check this. When we add this number 5852, we can get Diophantine quadruple. This form, this extension is important because we know that every quadruples of this form is called a regular. And one of the main open problem in this field is every quadruples are regular. Okay, after this, we can ask how large are these sets. Until now, we saw a pair, triple, and quadruple. And we can easily say that we have infinitely many pair. So by using that extension, this one, we can get infinitely many Diophantine triple. And also by using this extension, we can get infinitely many Diophantine quadruples. Can we continue like this? Can we get a Diophantine quintuple? For this question, we should consider for the two cases, integer case and the rational case. Let me start with the integer case. As we saw before that, actually, by using that extension, we can get infinitely many Diophantine quadruples. Here we can give two examples. One contains the polynomials. These are the parametric families. One contains the polynomials, the other contains the Fibonacci numbers. And we can easily check that these two examples are the regular form. What I mean, if this is A, B, C, D for here, sorry, this is A, B, C, and by using this A, B, C, and RST, we can get this D plus or D minus. So these two examples are regular. Okay, so the next step to find the Diophantine quintuple, can we find the fifth number, fifth integer, to get a Diophantine quintuple? That was a conjecture for a long time. What was that conjecture? It's saying that the Diophantine quintuple does not exist. After that, after this conjecture, first they proved that in 2004, Stoella proved that Diophantine sextuple, I mean the 6 numbers, does not exist. And if there exists a Diophantine quintuple, there should be finitely many. After this proof, many authors try to find the number of possible Diophantine quintuple. That I mean, in up to 2004, they didn't know that the existence of Diophantine quintuple. And 2016, it's announced, and 2019, it's published that the proof of this old conjecture, which means there are no Diophantine quintuple. So with this conjecture, the proof of this conjecture, how large are these questions is completely solved for the integer case. What about rational case? Okay, we cannot get a Diophantine quintuple. That means we cannot find the 5 integer numbers satisfy the same property. Can we find the 5th number as a rational numbers? So we should consider the rational case now. Euler showed that the Fermat set, this 1, 3, 8, 120, this can be extended to rational Diophantine quintuple by adding these numbers. And also he showed that there exist infinitely many rational Diophantine quintuples. And in 2019, Stoll proved that the extension of Fermat sets to a rational quintuple with the same property is unique. So that means we cannot find the rational Diophantine quintuple that contains these 4 numbers. We cannot find another quintuples other than this. So up to now we know that there are infinitely many rational Diophantine quintuples. So the next step will be rational Diophantine sextuple. Can we get these 6 numbers with the rational numbers that satisfy the same property? Actually, first example found by Gibbs in 1999, and these 6 numbers that satisfy the same property, that means the product of any 2 of them plus 1 will be square. And in 2016, it was proved that there exists infinitely many rational Diophantine sextuple. Okay, so we have 6 rational numbers, and actually infinitely many, that we can say these are satisfied the same property. What is the next step to find the 7 numbers? Unfortunately, this question, how large are these sets, it's not completed for this rational case. So there is no upper bound. We have to stop here because there is no Diophantine septuple as known. And not just the example, there is no any idea, there is no any conjecture. At least for quintuple, there was a conjecture. They believed it, the non-existence of quintuple. But for septuple, we don't know anything about this. Okay, these are the Diophantine n-tuples. And what is the connection between the elliptic curves? How can we connect these tuples with the elliptic curves? Actually, for this paper in 2016, they proved that the existence of infinitely many rational sextuple. Here is the idea. They use the triple, Diophantine triple, rational or integer, doesn't matter. And they try to do the extension from triple to sextuple. I mean, if you have a triple, you can extend this triple to the sextuple. Let me give this idea, the basic idea. If we have a triple,
Tuğba,
yes.
I'm sorry, I'm interrupting, but I'm just wondering that when I see Euler or Fermat, I'm just thinking about the algorithmic works of their works, and I don't understand the algorithmic base of your speech, but is there anything that we can combine it with graph theory or any algorithmic thing?
I don't know about the graph theory if there's a connection or no. Just there's the I know there is the connection with elliptic curves and the double points on the elliptic curves, and we can connect the divisibility by 2. That is the title of my speech.
Yeah, I think I get it. Thank you. You can continue.
Okay, so we can see how they are trying to do if we have an ABC here. Okay, and then we have 3 equations as here. So if we try to extend this triple to quadruple or quintuple or sextuple, doesn't matter, at least to find a one number, we need to solve this equation. This x will be our 4th number if satisfies this system. Okay. And after this system, we can assign to this system the elliptic curve, which is y square equal to x plus 1 b x plus 1 c x plus 1. And we say this elliptic curve is induced by the Diophantine triple ABC. Here we can observe that if any x satisfied this equation, system, that x should be one of the x coordinate of one of the point on the elliptic curve, because we know that this will be square, this will be square, and this will be square. So this will be that x will be one x coordinate of one of the point on the elliptic curve. Okay, by using this elliptic curve, if we see again, we can find trivial points on this elliptic curve. What are these zeros? -1 over a, -1 over b, -1 over c, which is here, and the y coordinate will be 0. These are the 3 rational points on E of order 2. What is order 2? That means 2 times A or A plus A will be identity on the elliptic curve, because we know elliptic curve has the abelian group structure. Another obvious rational points is P and C. P is 0, 1. If you take just the x equal to 0, you will get 0, 1. The other S is a little complicated, but not much, by using this equalities, these equations. Okay, after this is not obvious, but we can easily check by using the computer program. This S is equal to 2R, where R is this point is here. Okay, so we know that this S is a double point. Okay, why did we see these points? Actually, in this paper, as I told you here, this paper, to extension from triple to sextuple, they are using exactly these points, mainly this S. There are many tricks, there are many facts from the elliptic curves, of course, but they are mainly working on the double points and trying to find a specific point. So it is clear that every rational point, as I told you, a rational solution of the original system induces a rational point on E. The main question is which rational points on E induce a rational solution of 1. So that means, okay, if x satisfies this system, we know that x will be x coordinate of one of the points on this elliptic curve. What about the inverse? If we take any point on this, x coordinate can satisfy this system or no? Of course, it will not. So we are trying to find a special point on the elliptic curves satisfied. The x coordinate will be square x coordinate. When we evaluate here, these 3 will be squares. See? Okay, the last definition for this section, we can mention the quintuple, because mainly I will mention the quintuples on the last section. If we replace the number 1 in the condition AB plus 1 is a square by a fixed number Q, we can get a new definition, which is the quintuple. Let me introduce this one. Let Q be an integer or rational number, doesn't matter. A set of m positive integer or rational from a1 to an is said to have the property dq if ai times aj plus q is a perfect square for all ij from 1 to m. Here I cannot be equal to j. This is the same. Otherwise, we can call strong. So the main difference is just to change this 1. Instead of 1, we can adjust a q. Such a set is called Diophantine N with the property dq, or basically just we will call dq n tuple. Okay, we saw Diophantine n tuple and dq tuple. Now we can continue with the main part, what is the more details with the elliptic curves and the quartic models. Let's see first the models of elliptic curves. Let me start with the Weierstrass equation. This is an equation of the form, which is here, where the coefficients from A1 to A6 are coming from the field K. And we can associate to such equation the invariant C4, C6, and discriminant, which are the polynomials in A1 to A6 with the integer coefficients. These three satisfy this equality. Okay. Main thing here, we will talk about the discriminant, because discriminant could decide to many things for this equation, decide if this will be a smooth genus 1 curve or no. If discriminant is non-zero, then this Weierstrass equation describes a smooth projective genus 1 curve with a k-rational point at infinity. Point at infinity means the identity element. This will be identity element of this group structure. So in this case, if discriminant is non-zero, this equation will be an elliptic curve. Okay. And we know that if characteristic of K is not 2, then Weierstrass equation, this equation can be written as the short form, which is y squared equal to x cubed plus ax plus b, where ab coming from the K, our field. Okay. So this is the one model that we saw, which elliptic curve described by the Weierstrass equation. What is the other elliptic curve? First, I should give the definition of quartic model. This is an equation of the form y squared equal to pxy equal to qx, where p and q are the polynomials of degree 2 and 4 with the coefficients in k. What do we know about this quartic model? If we have this equality, which is qx plus px squared over 4 satisfies, is equal to this polynomial of degree 4, then we attach to quartic model the invariant C4, C6, and discriminants. C4 and C6 can be found by using I and J, which is written in terms of the coefficients of this polynomial. And for the discriminant, this is exactly satisfies the same equality with the Weierstrass equation. Okay. So for these models, we know the discriminant, we know the invariance. We have C4, C6, and discriminants. Okay, what can we say about this quartic model by using the discriminants? If discriminant, we can say the same thing, by the way, with the Weierstrass equation as the same way. If discriminant of this quartic model is non-zero, then this model describes a genus 1 curve C, let's say this is C over K. And if there is at least one rational point on this curve, that means the set of k rational points of C is non-empty, then this quartic model describes an elliptic curve. And if characteristic is not 2, a characteristic of our field K is not 2, then this quartic model can be written in the form y squared equal to px, where px is the polynomial of degree 4 with the coefficients in K. Okay. So up to now, if we compare these two models, we know that the discriminant can say something to get an elliptic curve or no. And if characteristic of K is not 2 or 3, we can get a short form. We can say this is the short form or the quartic model. And one more thing, the relation between this C quartic model and the Weierstrass model. If C is smooth genus 1 curve over the field K, and the characteristic K is not 2, this defined by a quartic model, if this C is defined by a quartic model, then the Jacobian G, this is abelian variety of C, is an elliptic curve that can be described by the Weierstrass equation, which is here, where the C4 and C6 are the invariants of the quartic model. And moreover, if CK, if there exists at least one K rational point on this quartic model, then we know that the C and J are isomorphic over K. So with this fact, we can see that quartic model, if there is a point on this quartic model, we can get a Weierstrass model with this quartic model by using that quartic model. Okay, up to now, we can say these two models seems so almost the same. There should be a difference because we are saying quartic model, elliptic curve described by quartic model. The other one is elliptic curve described by Weierstrass equation. So what is the main difference between these two models? The main difference is the group structure. Because we know that the elliptic curve described by the Weierstrass equation has the abelian group structure. That means if you take any 2 points, P1 and P2, if you want to add these 2 points, there is the exact explicit formula to get this addition. And this addition actually defined by the tangent process. but this is another field. So unfortunately for the quartic model, we don't have a group law. First, we should put a group law on the quartic models. How can we use this? Actually, we know that from the last fact, this C and J, which is this J is the elliptic curve described by the Weierstrass equation. So there is an isomorphism between C and J. So for the group law, we can use this isomorphism. Okay, let's start to define the group law first. Let K be a field. We will consider the quartic model y square equal to f of x, where f of x is from the kx and the degree of f is 4. And of course, discriminant of this model, this quartic model, should be non-zero. Actually, this discriminant, non-zero discriminant, is equivalent. The f of x has no multiple roots. And this quartic model describes, after these facts, these informations, this quartic model describes a homogeneous one curve over K. And let's say this is the Jacobian of C, will be denoted by E. Another information about this quartic model we can mention. From now on, we can assume that the set of rational numbers on this quartic model is non-empty, and this allows us to suppose the leading coefficient or constant term of f of x is squared. Let's assume the leading coefficient of f of x is squared. Let's say this is a squared, and then we can introduce the points at infinity. There will be, let's denote infinity plus and infinity minus these special points we will call points at infinity. These are here, 1a0, 1 minus a0. Okay, this is in the projective space. Okay, now we can give the group law actually. First of all, we have to fix a point P and on the quartic model, a point P, and we need to take an isomorphism. This is K birational isomorphism phi P for, between C and E, such that this P must go to point at infinity. This isomorphism satisfies this. We are choosing that explicit isomorphism such that this P goes to point at infinity. And then this isomorphism may be used to define an abelian group structure on C as here. If you want to take 2 points, Q1 and Q2 on the quartic model, and if you want to add these 2 points, first we have to go to E under this isomorphism as here. And then we can add these 2 points easily because we know this E has an abelian group structure and we know explicit formula for the addition. After we add these 2 points, we can come back to C. So this will be sum of these 2 points. And with that P will be identity on this group structure. Okay, this is the group structure on abelian group structure on the quartic models. Another important things actually we will use for the double points. If S is MCK, what does it mean? S can be written as the sum of Q n times Q. Q is any point on the rational on the quartic model. So that means this identifies NCK with NEK. What I mean is, if you take in a double point, which is 2A, on E, when you check the pre-image under this isomorphism, this point will be double point on C. Okay, now we can continue with the two divisibility on curves, and I will try to explain why we need to get divisibility. First, we can mention what we know about the divisibility by 2 on the elliptic curve, which is described by the Weierstrass equation. In order to show that this quotient is finite, we need to pass from a point P to a point Q, such that 2Q equal to P. And this process is called true descent on elliptic curves. Elliptic curves, which described by Weierstrass equation. By the way, from now on, I will not say all the time Weierstrass equation. E means elliptic curve, which described by Weierstrass equation. C will be elliptic curve or quartic model. Okay. And the true descent theorem, actually mainly, this is giving a necessary and sufficient condition to say that this Q is K rational point on E. Moreover, we know that by this theorem, true descent theorem, this gives us, if E is described by the following Weierstrass equation, which is here, x minus a1, x minus a2, x minus a3, ai's are distinct. And if you take a point P on this elliptic curve, which is x0, y0, we can say that this point is double point, or in other words, this is divisible by 2, if and only if three elements, that is x0 minus ai, are squares in K. So we are just considering the x-coordinate of this point. And if when we evaluate these linear terms, if these three linear terms are square, then we can say this point is a double point. Okay, this is the way to say, to find the double points on the elliptic curve E. That means from the Weierstrass equation. But we are interested in the quartic model, and we know that now we have a group law, so we can put some same criterion for the quartic model. Let's start with this quartic equation, which is y squared equal to, as here, linear terms, and we can assume that bi over ai are distinct. That means there is no double root, and this describes if there is no double root, multiple root, that means the discriminant is non-zero. And we can easily find one rational point here, which is minus b1 over a1 and 0. So this describes a genus 1 curve. Let's say this is C. By fixing a rational point P, we can actually, to serve as an identity element of this P will be identity element of our group law. We can find a similar criterion for the divisibility by 2 on elliptic curve, which is CP. Okay. Our curve C and identity point is P. Okay, now we can summarize what we have until now. Let K be a perfect field, characteristic different than 2. Now we can consider this y square quartic model, y square equal to f of x, where f of x is the polynomial of degree 4 and the coefficients in K and no multiple roots. So up to now, we know that the discriminant is non-zero and we can find the rational point. This is actually elliptic curve, genus 1 curve. And also we can assume that this f of x splits completely in K. So from these informations, we can write this equation, okay, where this quotient will not be in the K. So this is just to say these roots cannot be equal. So that means there is no multiple root. So this describes a smooth genus 1 curve. Okay, let's denote fix for each linear term here. We have linear terms, so we will call this as f1, f2, f3, f4. And the zeros of these linear terms, let's call this a ci. Now we fixed out a K birational isomorphism phi. We know there is a isomorphism from C to Jacobian of C, such that isomorphism x0, y0, this point goes to point at infinity. As we told before, this is our P actually. And this P, our specific point, is chosen to be different from the point Qi, which is the zeros of this linear term and 0. Okay. And now we can define the following rational maps Gij under on E for all ij from 1 to 4. What is this? Gij, if you put P on this map, this gives us Fix0, Fjx0, and Fix coordinate of the preimage of P, and the same for the J. As we see here, actually Fix0, Fjx0 will be fixed. So this will be always here because of x0, y0 is the fixed points. We will just consider these products. And we can easily observe that if we consider the point at infinity instead of P, that means the point at infinity, preimage of point at infinity is x0, the x coordinate. So here will be Fix0, Fjx0. So that means Fix0 square, Fjx0 square. This is automatically square. So why did we define this? Actually, we will say that our criterion will come from this rational maps. This must be square. If you take a point Q, we will consider the preimage of this one as a P, and then we will consider this product must be square. What I mean, I will try to explain on this theorem that we proved. Let C be smooth genus 1 curve over Q defined by the equation of the form as here. These are the same thing. And we need to assume AI is not 0. If we take a birational isomorphism from C to Jacobian of C with a specific point x0, y0 goes to point at infinity. Okay, up to now, these are the same what we saw. If you take any point Q on this quartic model, and if you want to say this Q is a double point, here is the criterion. This point is double point if and only if this product must be square in the rational numbers for all ij. Okay, that's why we put this one. Actually, we defined Gij for the proof of the main theorem, but I will not be able to give all proof. And we are using this Gij to prove some proposition before this theorem, but just I wrote it here. This is exactly same as here. Okay, now we can see some examples. Let's first we need to take a birational isomorphism. Let's call this as phi1 as given here. Let's see, we defined our perfect field K by the following quartic model, which is here. And this birational isomorphism from C to E is defined by here. I mean, if you take a point U and V that pairs, and you will see the image of this UV as X and Y on E, okay? And also we can find elliptic curve, which is described by the Weierstrass equation by the coefficients A1, A2, A3, and A6, okay? So we can see the explicit E. And the inverse of this map is given by here. That means from E to C, if you take a point XY, this pair on E, you can find the coordinate UV on the C, sorry. So these are the explicit formula for the isomorphism. Another important thing for this isomorphism, in the view of the theorem 1, this point, our specific point x0, y0 will be 0, q. Because we know that under this isomorphism, the only point 0, q goes to point at infinity. So from now on, our important numbers is x0 because our product has fi x0, fj x0. So this x0 will be 0. Let's see the example. Here is the C quartic model, which is defined by here. And we can consider the phi1 as I give previous part from C to E. We can find the explicit elliptic curve, which is described by the Weierstrass equation as here. Okay, let's start with a point T on the C, which is here. And we are trying to, now we will try to find a double point of this T. What we need to do, first we need to go to E under this isomorphism, which is here. And then we have to take a double of this point, or you can just sum these two points itself. And we can find this double point, but still this is on the elliptic curve here. So we need to just go back under this isomorphism with the inverse of this isomorphism. So this point will be 2t. If you start with t, 2t is here. So the main thing we will interest here, the x coordinate of this double point, because we need to evaluate this point on the each linear term. So which is minus 56 over 55. Let's evaluate this point on the each linear term, which are here. Okay. When you check these two product, any two of them, when you product any two of them, you can easily observe that these are squares. Why it is true? Because we know that fi0, which is here, if you put 0 here, this is 1, this is 1, this is 1, and this is 1. So we don't need to check fi0, fj0. So this will be always 0. And this will be always 1, sorry. So it is easy to see that the product of two of them will be square. So that means Gij that we defined before, this will be square for all ij from 1 to 4. So as we see, if you start with a double point, this part is this side is correct. We can see the same side for the on the another example that when you put 0, x0 is the fixed, by the way, still 0. When you put 0 here, this is 2, this is 4, this is 8, this is 9. So it will not be same. Let's see what is happening here. Okay, this is the quartic model. And by using phi1, again, we can find E. And if you start with the t minus 5, 6, we can easily find the 2t by using the same way. Okay, first go there and the double point and then come back. So the main thing we will interest is the x coordinate of this point, which is minus 64 over 7. Okay, we need to evaluate this x coordinate on each linear term as here. But as you see here, the product of any two of them is not square. For instance, f1 times f2, this product, these two rational numbers, the product of these two rational numbers is not square. Why is that? Because we know that f1 0 and f2 0 is the product of these two of them is not 0. But 2 times 4 times this number and this number will be square. This is the same for the other one. That means fi0, fj0, fi are x coordinate, fj are x coordinate. This will be always square for all ij. Okay. Okay, now we can mention, excuse me. Oops. Okay, we can mention for torsion points on the quartic models. Okay, for torsion points means if you have a point P, for P will be identity. We can give a necessary and sufficient condition to say there exists a four torsion point. Okay, let's see defined as here. And then this point from C to E is defined as above. We took that isomorphism. Then C is the four torsion points over Q if and only if one of the following is false, which is depending on just the coefficient of these linear terms. Okay, K1, K2, K4. Okay, and now we can see the proof just maybe fastly without much details. By using this phi1 isomorphism, we can find the elliptic curve specific, the explicit elliptic curve described by the Weierstrass equation. The coefficients are here, A1, A2 from to A6. Okay. And now by using Magma, the computer program, we can find the two torsion points on E. That means 2 times P2 is point at infinity, and the same and the same for the other P3 and P4. Okay, these are the two torsion points. For this one, we need to consider the preimage of these points as here. If the preimage of these points are the double point, that means these are the four torsion points. To say the double points for this one, we need to use the theorem 1. So the x coordinate, let's consider this one. This is U2 and V2, which is here. This is double point if and only if when you evaluate U2 for each this product from the first condition, this must be square. So this one will give us the first condition actually. By using this point, we can get the first condition. Two of them, both of these products must be squares. So this point will give us the first condition. The other 2 points, this in P3 and P4, will give us the other 2 conditions. By using this for torsion points, that theorem, we can see one example to say that there is no four torsion point on this quartic model, which is here. We can skip just some detail because of time, I think. Okay, let's see a smooth genus 1 curve QST defined by here. This is 2 parametric families, 2 parametric smooth genus 1 curve. Here is T and S cannot be 0, T plus S cannot be 0. Okay, if you put this as K1, K2, K3, K4, we need to consider the condition 1, 2, and 3. These are the conditions. After these conditions, we need to say, to see the first one, both of this and this must be square, and these are the same. Okay, just I will give the third condition and skip the first and second one. By the third condition, and for this one, if you want to see this is square and this is square, we know that the denominator is square. So we need to get T times 2S plus T, which is here, and S times S plus 2T, which is here. These must be square. If these are square, if and only if, these two are square, if and only if there is a four torsion point on this curve. But you know that if you are trying to find these two, the solution of these two equations, this is the intersection of two quadratic surfaces here. And we know that this intersection will give us elliptic curve described by the Weierstrass equation, which is here. And the model Weyl group is isomorphic to Z over 4Z, and the corresponding points STUV, which is here. Okay. But here there's a problem because with this corresponding S must be 0 from here, and the second one T must be 0, and we assume that S and T cannot be 0. So by the first condition, we can say there is no four torsion points by using the first condition. And this is the same by using the I'm sorry, this is the third condition. By using the third condition, we can say it's not coming the fourth origin point, and this is the same by using first and the second condition. This is the same way. Okay, the last thing I want to mention about the polynomial DQM tuples. First, we can give the definition of polynomial. Actually, this is the same definition, just we need to extend our ring to the ring of polynomial. Let K be a non-zero polynomial, and these numbers, these polynomials, be the set of m non-zero polynomials with rational coefficients. And this set is called polynomial DQM tuple if AI times AJ plus Q is Bij squared. These Bij is the polynomials for all IJ from 1 to m. What do we know about these? We will be interested in the polynomial DQM tuples whose the elements are linear polynomials, and Q is also a linear polynomial. Now we can define L1. This is the supremum of the cardinality of S. S is the polynomial of the AX plus B triple, consisting of the linear polynomials for some AB. And we know that it was shown that the supremum is 4. So that means if we have a Diophantine, if we have a polynomial DQ quadruple, this quadruple, which is here, this cannot be extended to D16x plus 9 quintuple by using a linear polynomial. Okay, but we can show that for infinitely many. Yes.
I'm terribly sorry for interrupting, but we have just 1 minute, but we can give you some extra minutes to finish your speech. I'm sorry for not warning you, but
no problem.
As I can see, you have lots of slides, so if you can finish your presentation, right? Yeah.
Okay, just I need 5 minutes to skip the last parts.
Okay, that's great.
Okay. Okay, for here, we know that this cannot be extended by using linear polynomial, but we can extend for infinitely many x. Okay, this is the basic corollary from the theorem 1. What is this? These are the same. Just if we assume this fi x0, fj x0 is squared here, so we can say this q is double point if and only if there is a delta q, which is satisfied this one. Another corollary is related to this extension actually. If delta q, which is the same as in the corollary 1, this delta q is squared, then we can say that if we start the Diophantine quadruple, then we can say that we can get a Diophantine quintuple by using this quadruple. So from this one, from these two corollary and the main example, we can see this quadruple can be extended to rational quintuple for infinitely many t. Okay. Okay, I will skip the proof of this one because mainly we are using to find this delta q. Here we found this delta q actually. This should be a square. So in the view of the corollary true, if this is squared, then we can get an extension from quadruple to quintuple. But how can we satisfy that? How can we say this is a square? So that means the denominator must be square. If this denominator, if we rewrite this, we can get an elliptic curve, which is described by the Weierstrass equation. And if we see the model Weyl rank of this elliptic curve, which is 2, that means there are infinitely many points on this elliptic curve. So that means there are infinitely many t's such that this delta q is a square. So after that, we can get this Diophantine quintuple. Let me remind again, we started with this quadruple. We can find this the fifth number. Here is the some table. If we use this t, we can get this quintuple. These first 4 numbers given by the main theorem actually. Here is this, and we can also find another such examples for this one type of quadruple. For instance, this quadruple can be extended to quintuple by using this elliptic curve because this model Weyl rank is positive. And this is the same, the second one, third one, and the fourth one is here. And the last thing, by using the third one, for instance, this quadruple to extend the quintuple, if you take t is this number, and if you put here, you will get this is q squared. And our quintuple, just we use the theorem, the second theorem, to get this quintuple. On the other hand, we know that if this is q squared, there's another theorem says that xi times xj plus q squared is equal to yij. If you have 4 rational number, you can easily find the fifth number by using a and b, which is here. So from the one paper, which is written before that, we can find another number. So this is coming from this paper, and this is coming from our paper. So we can get almost sextuple, almost the q square sextuple. Thank you for listening.
Ma'am, thank you for your excellent speech. It was very informative, and I think for the ones who's studying in bachelor's or in their masters, it was very encouraging for them, because what you're doing here is something that is a great example for all of us. And now there's one thing left to do. Could you please close your presentation? It's time to take souvenir photo. Aybüke, can you take the photo? Thank you. But it was an honor for us to have you here and listen to your speech. It was excellent. Thank you again and again. I think that's all for today. Today's session. And for our attendees, we're waiting for you to attend the next speech as well. And I'm sure that it will be as great as Tuğba's speech. So please attend the next one as well. Tuğba, that's all for now.
Thank you so much.
Do you have anything to add up?
No, thank you.
Okay, that's great. Arkadaşlar, bu session bitmiş bulmakta. Tuğba'ya konuşmaları için çok teşekkür ederiz. Gayet bilgilendirici ve ufuk açıcıydı. Artık